Well, I have a wonderful electronic invention I want you to see.
It looks something like this.
And welcome back to creating the logic behind the Railsystem. When you clicked on the video, you probably have seen that it is fairly long. On the one hand, I wanted to keep each video short, but the nature of this section makes it almost impossible to cut it into really distinct sections. In this video I'm doing nothing else than to work on a single wrangle. But that wrangle is one of the key elements of the whole project. When it comes to the rail itself, this will decide where everything will be placed. It takes in all the points of the rail, points that already have the information what objects can be placed at its current height, what specific towers or bridges can be built at each location. You can see those attributes here in the viewport. When I'm done with this wrangle, and with it chapter 4, we will have a solid distribution of the several tower options along the rail, minimizing overlapping between towers and their support distribution. Or in more simple words, this wrangle will figure out where to place towers without making it look ridiculous. In the last clip, I prepared the wrangle with a simple framework and comments to outline what steps I will need to take to implement this. So let's head back into that wrangle and do the actual picking of an option. We already have a solid start. We are looping over the points available and are looking for a point that does not have any support yet. Once we do find one, we want to check the available options and find out where we would place those options. This is going into its own function and I call that check options. That function doesn't exist yet, but what I want to do with it is to fill these two arrays that I declared last time. That means I'm sending these two as parameters with the function. In addition to that, I'm also putting in the counter of the loop, which basically allows me to know what is the current point. Now let's write the check option function. First of all, it will be a void function. That means it's not returning a value, unlike the point function, for example, that returns an attribute. This function's only job is to do something with the two arrays I provided. Another thing you should know about custom functions is that by default, all your parameters get passed as reference. That is a fancy way of saying whatever I change in here will also affect the array down below where I called the function. This array is not just a copy, but exactly the same array. But here in this function, I don't have to name it the same way. The second parameter is the position array, and Houdini will keep track of that. But if I want to, I can use a different name, just positions, for example. And the counter does really hold the information what is the current point. Just don't get confused and mix your names up. And that's a good reason to keep your namespace the same throughout your project. One backdraw to push chunks of code into functions is that you don't have access to other variables outside of the function. For example, I'm going to need the strength levels again. I could put them all into the function as parameters, but it is much easier to just create them again if you need to. I do need them, so I copy and paste them into my function. If you keep the names of the channels the same, they will get their values through the same channel, and the UI will only create one channel for each name. Besides the strength levels, I also need a weight value for each option. I want to use that to manipulate the probability for a specific option. Just rename the variables and the channel names in a way that make it obvious for yourself that these are different values. Now we need to do some thinking. The check option function is called whenever we have a point without support. Let's say we are currently on point 10 and its support attribute was 0. Now we want to know if the level 1 tower is allowed to be placed by reading the tower 1 checked attribute. But we don't want to know that for point 10. We need to look at the point that sits at 10 plus the strength of level 1 minus 1. Why, you ask? I will tell you, dear audience. Let's assume we give our tower a strength of 5. And as I explained in earlier clips, my system for strength distribution is very simple. A tower with a strength of 5 means the point gets 5 support, and its direct neighbor gets 4. the next one 3, then 2 and 1. If I land on point 10 and it has 0 support at the moment, you can bet that point 9 does have some support. Placing the tower on 10 would spread unnecessary support over to point 9 and beyond. But by placing the tower on point 10 plus 5 minus 1, so 14, the tower will spread its support while just covering point 10 with 1 support. It is a simplistic approach to distribute support along the rail, but it does create good results. We do the same with all available options, and by adding their different strength levels, we adjust the appropriate position that needs to be checked. After we found these positions, we need to do some additional testing. For that we need some additional variables, and while we know that there's probably not any support between our current point and where we would place a tower, we don't know that for what is behind the tower. We want to discourage placing towers right in front of a tunnel, for example. So we check if we are allowed to place tower 1. We want the check variable to be 0 at this point, and then loop over a specific number of points. In case you have a setting where you have random points with support on the rail, maybe you want to place some towers manually before this logic runs, then you would need to start this at current, which would be at 10 when you take my previous example. But I do not have that, so I can skip those iterations by starting at 14. The loop should continue until the tower shares support. So our tower on point 14 would cover up to point 18. Which means the loop should continue as long as I is smaller than. Here we start with what got us already to point 14 in the first place and add another strength value. But we need to decrease that by 1 again, which makes this minus 2. So the result will be 18. Then, for each point that we encounter, we want to make sure that all of them don't have any support. For doing so, I check if the result of the point function for that attribute is not equals 0. If a point is not 0 in its attribute, I want to react and change the check variable. I can also cancel the loop with a break at this point. I already know that this option doesn't work here. It means that I come too close to something that has support. In my example, that should be a tower or the border. Short notice, I do cast the result of the point function to be an integer here. I often do the cast for a point function by reflex, but you don't really need to do that here. You mainly need to do a cast when it's not clear what data type is expected. But it doesn't harm anything, and you are just telling the system, hey, that thing that is an integer, it is indeed an integer, while the syntax says, yeah, I know. And don't worry, the system will tell you if you need to do a cast. In case I don't find any support, I'm safe to mark this option as available, but I'm not just activating it. I could just place a 1 in the option array and later look up which index has 1s. I want to bring in the weights I defined. To prepare that, we are going to save the weight of the option at the index I reserved for it. So the weight of tower 1 goes into index 0 if it's allowed. The position array is getting the point number where the tower would be placed, the 14 of my example. Now I only have to copy and paste this block for all the options to make the same test for each of them. By doing that, I end up with an array holding the weights of all possible options and one array with their positions. And I just noticed that I missed the increment step for the for loop. I++ it is. Let's generate the UI elements for all the channels we set up and feed in some values. For the strength levels, we could start with 3, 5, and 8 for the towers, while the bridge will provide something much bigger, let's say 20. For a start, I keep the weights at a neutral state. We need to set that up first, anyway. So far, we only saved the result in array variables, so we can't really see what it does. I like to print out the data at these stages to check if I'm on the right track. In my case, it would make sense to look at the point number, and both arrays. So let's print the following. Test %d, the placeholder, options, placeholder, positions, placeholder, /n, which you need to create a new line with each print. Then paste in the variables, and now let's take a look what we get. And that doesn't look bad. We see tests for all points of the segment. It seems to prohibit level 1 and the bridge a lot. Let's check if that is indeed correct. And it seems so. Yellow and red stands for level 2 and 3, where we can see a lot of 1s in the viewport, while the two bluish values are mostly 0. Those are the level 1 tower and the bridge. As another reminder, the reason for that is that the rail is probably too high for level 1, the tower being theoretically too small to hold the rail, while the rail is not high enough to place a bridge. Now let's look at the positions. The very first point is number 5. Since we do have a border strength of 5, which creates initial support on the first 5 points, and since that sounds weird, I'm just saying it once more for those not as familiar with the fact that points start at 0. So point number 5 would place tower level 2 on point 9. I set it to have a strength of 5, so that's correct. Level 3 lands on point 12, which has a strength of 8, so that's correct as well. So let's do some experiments to look for flaws and errors. If I change level 1 to have a strength of 20, suddenly point 5 has the green light for level 1. If you refer back to the viewport, there are indeed some 1s for level 1 that by incident are within the reach now. If we switch the high value to the level 2 tower, the result adjusts and it does seem to do the right thing. But what happens if we exceed the range of the segment itself? Just to test that, we could turn tower level 2 to a value over 200 support to distribute. As you can see, that makes this option invalid. But that's not because of the support check. The support check would have caught the moment we reach the end of the segment, since we would find support coming from the tunnel. But what already catches this case is that I can't find a tower 2 checked attribute for the points that are out of bounds. But now let's head back into the code, finally implementing the actual picking of an option. I would say we grab that print and put it a bit further down behind the picking. Here we call another custom function. Let's call that pick option. This time we do expect a return value. It will return the actual picked option, the index of the equally called array. It will use the same parameters as the check function. Later we want to see what the system is going to pick, so I'm going to throw that into the print as well. Now the plan B comment is no longer in the right place. That workaround is also going to happen somewhere in the pick function. But first let's do what we can right here. How can we react to the value the function returned? First we need to check if there's anything useful in there. If we didn't find a pick, it is probably still -1. So we only continue if it isn't that. Then we really want to apply strength and support. The point where we want to apply them is in the position array. The support value would be the strength we defined in the channels. And I will need an identifier which strength option this was. This will be 1 for tower 1 and 4 for the bridge. If the name strength is a bit confusing, you can call it any way you want. Option, type or bacon, whatever suits you. But the used index in the array, as the used variables for support and strength, are dependent of what is inside the pick variable. So we need to create an if condition for each of our options. If pick is 0, we want to place a tower level 1. That means the array uses 0 as index. So we need to use the variable from the level 1 channel. And strength is set to 1. There can only be one valid pick. So I add the if condition with additional else if blocks to cover all possible outcomes. Here it doesn't make a difference over 4 individual if tests. but it is a good practice to cover your bases whenever you can, meaning try to build your code in a way that it only accepts, or rather works with the data you expect it to have at a given point. I break that practice often enough myself, but I try to keep it in mind. I want to take a quick look at how this will react at the moment, but to make the syntax correct, I will need to implement the pick function first. At least create the bare bones of it. As I said, the plan B command needs to follow along into the pick function. We want to return the picked index, so an integer. And we again have the same parameters as before, the two arrays and our current point number. Somewhere in here we will create the plan B, and in the end we'll return our pick. But in case all we do here doesn't work, we want to make sure that pick starts out with -1. This will result in a lot of printed statements. There you can see them go. Let's stop the processing for now. It looks like it's an endless loop, but that's not it. It just needs to print out a lot of lines. We do have the sub loop that creates 115 iterations with this segment. And the wrangle does create another 115 iterations. And it does so again and again for each new subloop iteration. But without the print, this would still be finished almost immediately. Obviously, we don't need to do all of those iterations, but it makes sure that we are able to reach all combinations. And the first, most important factor to find what we need is to make a choice what is picked. Let's just hardcode pick to always be 1. And this does create a funny result in my current scene. It does that for two reasons. For one, it is bound to the distribution. As you can see, the print says it does test 0.5, sees 0.9 as valid position for option 1, and then picks option 1, since we deliberately said it should be 1. If the support from 0.9 never gets distributed, 0.5 will always keep its 0 in support. 0.9 will always be the position for tower 2, and since we fixed the pick on 1, this will never change. But currently, even if I already had distribution, I sneaked in a change as an experiment. It resulted to be a flaw in the system, but I kept it in so I can show it to you right now. This is a good opportunity to reflect on what the system does so far. Why it reacts funny, and overall, aside from the project, give you a better idea on how loops, data and conditions work with each other. I did change the following. In my recording of the check function, the for loops start at current plus level -1. So in my example of 0.10 having 0 support, it checks 0.14 to place a tower with a strength of 5. Once the system works with all its bits and pieces, if there's a tower on 0.14, we wouldn't even test on 0.10. It would already have support. So I figured I could skip the -1 and basically ignore 14 and start at 15 to check for support. But doing that would be another obstacle just in case you want to place additional support by hand before you let this calculation run. So the most accurate approach would be let the loop start at the current point and do the tests beginning with the first point without support. Again, as an example, if your current point is 10, you have the strength option of 5. Just test from 10 to 18 to be sure that everything is clear. Maybe we want to use the Python state from the trailer to place something first and then let the rest be calculated. But for this part, the main priority is to prohibit overlapping support. So I keep it like this going forward. But as I said, we can progress much further without implementing the support distribution. So let's do that now. We need to do something with support, and we already have a variable for it. After we used it once in the starting condition, we can do something else with the variable. After we have done something specific to the picked option, we can now save the available support of that option, because that is what we want to distribute over the neighboring points. But to do that, we also need to provide the position where we wanted to place the tower. That was in the position array that we have manually written in each branch. But if you look closer, you might have already seen it. we didn't need to specify which index the position array needs. That was one of the reasons to use arrays in the first place. The variable pick always has the correct value regardless what was picked. For now I can keep the fixed pick of index 1, but I push that over here into the pick function, where it feels more suitable. And now to the distribute support function. It doesn't return anything, so it's a void function. We have the index and the support value. Both are integer. I will have 2 for loops in here to spread the support. And because I feel like it, I declared the counter right at the beginning. The first loop is going to distribute forward. So again, I tested on point 10. I placed the strength 5 tower on point 14. That means now I will start to apply support on point 15. And I keep going as long as the counter is lower than my current point plus the support. I start on point 15 and it is supposed to get 1 less support than the tower has itself. So how can I write that in a way that I always have the correct difference for each point? I take the support I was starting with and then subtract something. And that is the loop counter minus the index. By now the example of point 10 should be burned into your brain, so you might remember that the last point to get support from this tower is point 18. So in this formula, the y is 18 and the index 14. The result of that is 4, so we have original support 5 minus 4. The value is now added on the support attribute on all points coming behind my tower. I add the value rather than set it, which allows me to debug it later and see if I made something wrong. And I do get overlapping support. But I want to stop this in case I reach the end of the segment. Again, nothing bad should happen in my specific case. All that would happen is that it tries to add a value to a point that doesn't exist. The set function would simply fail. This again can be filed under best practice. When something should stop, make sure that it does. Then we only need to copy and paste this block to go backwards. This part is going to cover the points before our tower. So 13 down to 10, where we found the original point with 0 support. So we only need to reverse all the values that make the loop go forward. We start at index -1, we stop when y is bigger than the stop condition, and we decrease the loop step. The stop condition for the loop now is if the counter is smaller or equals 0. And before I leave the code and give it another go, we should correct this mistake I made. In my haste to set the strength attribute with the variable pick, I left it adding the numbers 1 to 4. Pick already has the index values 0 to 3, so what each if branch should do is just use pick +1. So let's see what happens while we still always pick option 1, but have distribution active. Now we see a bunch of different points that get tested, and we also see that we get a number of points with the strength of 2 that provide 5 support. The basic idea is already working, but of course we don't want to always pick the second option. We want to pick what makes the most sense. That and what we prefer to place using weights. Let's go back into the pick function and fill it with life. There are a number of ways to implement random weight choice. And this is the one approach I settled on. First, I'm creating and initializing some variables. We have one to carry the sum of all weights, and then we want to access the original point number of each point. I save that in the attribute orig_id for original ID. Each segment will start with point number 0, and the second segment will have different IDs than the first. This should make sure that we don't replicate the same pattern with each segment. because we're going to use this original ID as a seed in a random value. Then we also want a global seed to influence the overall result. Some additional variables for the loops to come, and we can dive into it. The job of the first loop is to gather the sum of all weights. There's also an array function called sum that would have done the same thing. The next step is to pick one random weight between 1 and the sum of weights. To get a truly random value, I'm going to feed in the original point number here, the seed, and the current point into the rand function. That gives us a value between 0 and 1 that we can remap with the fit0run function over the range we wanted. The rand function created a float, but we need integer values, so we capsule this again with the rin function and the integer cast around that. This combination of rin, fit0run and rand is one line that I use very often in my projects. With this you could go into multiple directions. You could, for example, remap this value again to be one of the available indices. We have 4 different options, so let's say each one would have a weight of 2. This would give us a sum of 8. Then we would map the chosen numbers in a way that weights of 0 and 1 would be the first index, weights 2 and 3 the second, and so on. Since a higher weight has more possible chances, it would occur more often than an option with a smaller weight. That works as well, but I picked another approach. I am going to loop once again through my option array, and this time I'm taking the random weight I picked and I subtract its weight. One by one, the loop will decrease the selected value by the weights it finds in the list. And once the random value is lowered enough to be 0 or less, and the current weight is not 0, that will be the index we choose. Notice that this version of the for each loop does have 3 parameters. Usually you would only have the variable for the element, here the weight, and the array itself. But you can add an integer variable that will keep track of the current iteration. Once we isolated an index for our selection, we can break out the loop with the break statement. Now we can get rid of the hard-coded pick of the second option. From now on, we pick a random valid option using the provided weights. Be aware that this will start to spam the console if you still have the print command in place. It will feel slow since again printing takes its time. At this point we should be fine and we can comment it out. As you can see, the overall code is processed quite quickly. But do we get a reasonable result? And how else can we look at it? We established a system that does pick an option and applies its strength to the point. So now we can isolate those with strength with a blast node. If the strength equals 0, get rid of the point. So these are the points where the system will attempt to place towers. And by the number in the strength attribute, we can also see which option that would be. If we change the seed, we should notice that the points start to jump around, since other options get chosen and their strength levels also change, and therefore they need to be placed somewhere else to prohibit the overlapping. Let's take a closer look at the weights and if they fulfill their purpose. I give every tower the same strength, which would result in an even line of tower points. If we change the weights to prefer an option, we should see an obvious increase in its occurrence. When I tested it, I first thought I made a mistake, because tower level 1 wasn't occurring as often as I would expected it. But I missed an obvious reason for that. Tower level 1 has a limitation for the height it can cover. And in my current setting, they barely make the requirement. So for a true test towards the weights, I should increase that value. Again, this should be later controlled by the control node. And now we should see a lot more level 1 options in the mix. I'm happy with the way the weights are utilized and how changing the weights influence the chosen options. But there's a big drawback that needs to be addressed. A reason why we need to implement the plan B. If you look at this area with the valley, that's the key area where the system should place bridges. The distance from the rail to the terrain is too big for any of the towers. So the only possible solution should be a bridge. But as you can see, if I skip through the seat, there are variations where we don't get one. I think I still have a logic error somewhere in the way the pick function does the weight test. That will lead to a scenario where no weight is picked and no choice is valid. Then it does the next point and tests again. And again it doesn't get a result. Do that often enough and we reach a section where the bridge isn't allowed to be placed, since its support will reach the tunnel support. And honestly, I didn't even bother with solving this case completely, but it would be easy to do. If only one option is available, it should ignore the weights and just pick that option. That would be the solution for that. But I can solve this issue with my main reason for plan B at the same time. To get a better example, I isolate the segment number 2, a very specific area. We leave a tunnel hanging somewhere high up, way too high to build a tower, and then go straight into the next tunnel. Now we reach an area where the main system is already working, but you need to find solutions for the edge cases without influencing the main logic too much. And I went for something that solves this exact problem while also doing something for the missing bridge in the first example. It is not the best solution and might create other issues, but the end result in this combination is what I want from the system for now. If the system can't find a suitable option and leaves a number of unsupported points, I want to find the middle and try to place an available option there, ignoring the support overlap. So in cases like this, I would try to place a bridge right into the middle. It doesn't do that now, since the bridge has a support of 20 and would touch the points that are already supported by the tunnel. So let's tackle that last obstacle. We head over to the wrangle where we placed the plan B command. If the pick at this point is still -1, we either fell through our weight testing or we have the problem we just saw. Even though we have points with 0 support, we are not allowed to place anything without creating overlap. In that case, we go into a new function, the override pick function. It will get the current point and the position array and will return whatever pick it might give us now. Again, we initialize with -1. And now I want to find the middle of the unsupported area, because I assume that this will mostly come into play when I find these short segments hanging over a valley and we just quite don't get to fit in the bridge. I have no idea how many points I might need to check, so I could very well use a while loop. It would make sense, but if I can find an argument to do a for loop, I rather do that. I seem to find endless variations to create deadlocks with while loops. This way, even if the rest of my logic fails, at some point the loop will finish. And I know a limiting factor to have a hard border, and that is the length of the segment. There can't be more points than that. So I do a loop from current plus 1 until I reach current plus the length. That is of course almost always way too much, but I can just stop the loop once I have all that I need. And that is all the points that don't have support. That means I increase the counter as long as I keep finding points with 0 support, and once I find one that does have support, I break out of the loop. Another way for doing that could have been the findAttribVal count function. This would have returned the number of points with 0 support, so exactly what I was looking for, with the only drawback that I'm not exactly sure if all these 0 support points are connected together. Maybe I found 8 points. Then I want to place something on the 4th point. But am I allowed to do that? I still want to apply those rules. That is the remaining flaw with this way. I'm going to test if exactly the middle point is allowed to place a bridge or a big tower. But if there's any very irregular terrain blocking that middle point, the workaround will also don't find a valid result. But I think that should be very unlikely, or look very ugly in the first place. I steal that block from the initial check function. This will give me the available options of the exact point. Just replace the point number with current plus counter divided by 2. I'm going to create a new local options array to have all 4 options available. And I'm going to push that into one last function that I'm going to create. I pick the last option. Again, this returns the final pick, which will also be what the override function will return. It takes the newly created array and an integer for a specific point, the one that we also tested before. Don't mistake this array for any of what we had before. This is just an array to hold the results of the test. Whatever pick this will make, I'm also going to save that specific point in the position array. Finally, let's quickly implement this last function. We have the array and the integer. Now the current point will be the middle of the supportless points, and we return an integer. We keep the same framework, initialize the return value, and make sure there is a return. This time the array does not contain any weights. I chose to use the check attribute, so all available options will be set to 1. You could make this regard the weights by reading the weight attribute into this array in case they are allowed. But again, I'm almost expecting this to only contain the bridge in most cases. I'm using the max function to get the highest value saved in the array. That way I could easily make use of the different rates, but even if there are only ones inside, this function will tell me if there is an available option. Because with whatever I find, I will use the find function with it. This will give me a specific index where that value is saved in the array. So if it is the bridge, this will give me the index 3 for the 4th element. Let's take a quick look at potential typos or errors. And here is one. Parameters in functions are separated by a semicolon, and I did the same in the override function. Here it looks fine. And here I got confused with the naming. The pick function provides the option position array, but to prove a point, when entering the pick function, I used a different name, just positions. So in the context of this function, there is no option position, only the position array. A good example to remind you of this concept of local namespace in your functions. So let's see what we got. Already we have a different output. If you remember, we had examples where we had either no bridge or one bridge in this area. Now when changing the seed, we always get at least one bridge. That was the purpose of plan B, making sure that we always get that one bridge in these edge cases. The obvious drawback is that we might end up with a second one because we still have points without support. But I rather prefer to have an extra bridge point than missing them where I would expect them to be. Like in the previous example of segment number 2, we don't have the space to place a bridge with the normal rules, but plan B makes sure that there is one anyway. What can you do if this doesn't result in what you need? You can change the seed, the weights, or adjust your tower requirements. If you find your bridges to be placed in spaces that are too tight, let's say the segment would be even shorter. Maybe there is just one single point with zero support. With the current setting, the system would find that one point and use it as a middle point. It would still get a bridge. But you do have control over these decisions. You can simply increase the support that is provided by the tunnel until you don't get any unwanted bridge points in your segment. There is still a lot of space to optimize this rule set, make it more precise, and take more edge cases into account. But with this, the logic part to place the different objects is done, and we can proceed to actually create towers and bridges, all starting from one single point. the point where the system decided to place a tower. But that will be part of the 5th chapter.